All right, what is up, everyone? Welcome to week 64 of Chill Kernel Hacking for Fun. Get these headphones up. Hope everyone is having a great week. I am back at it, and we are continuing with the network driver, and in particular, we're working on the RX side of things. Cat Flare, what is up? Super punctual. Nice to see you. I'm gonna get it with the test 0, just for fun. Also on the Twitch side, test Twitch. Yeah. Let me just get set up really quickly. Currently writing code as always. Word. What kind of code are you writing today? Are you working on your Windows clone? Okay. You got audio, got music. Let's see how the music sounds. Test 1, 2, 3. So let's talk about what we're doing. Memory management, speed running to NVIDIA drivers. Nice. That sounds pretty challenging. I'm still over here doing the network driver. Yeah. Okay, so let's recap what I'm doing. I'm working on the networking functionality of the OS, and last time I was working on the receive side of the NIC, which is kind of similar to the transmission side of the NIC, but like a little bit different. And I think last time I sketched out a bunch of code, which we can visit over here. That's at least part of it. I sketched out a bit of code. Here's the second part. Yeah, I sketched out what it would look like to initialize the receive side, but I didn't have enough time to actually test it and get it working because QEMU was giving me issues last time. But I believe I have since fixed all of those issues and with QEMU, and can now proceed with actually debugging what's wrong with the receive side. So just as a recap, the receive side involved a couple things. We need to allocate memory for the receive ring buffer, and also allocate memory for some backing buffers that each receive descriptor will point to. And that's pretty easy. I did it just in a very dumb way, just like I did the transmit buffers, where I'm just statically allocating the memory. However, unlike the transmit buffers, I'm using a lot more descriptors. The ring buffer is way larger for the receive side, and that's actually because they explicitly told me to do that. It says you should use at least 128 receive descriptors. So that's what I did. So that was part one. The second half of initializing the receive side is by setting a bunch of memory mapped IO registers to initial states. Like these two writes are setting the MAC address of the NIC. This is all just stuff I read from the manual. We have to point some registers at the receive ring buffer. we have to initialize the head and tail. Okay, actually I'm just going to delete this thing because I already did that. So we reset the head and tail of the ring buffer. We filled in all of the descriptors with empty and available descriptors, actually. And then we pretty much just enabled it, and it wasn't actually that hard. A lot of the initial state of the receive side of the NIC is actually how we wanted it to be, with apparently one exception. So I'm just going to stage this to kind of soft commit it. Yo, what's up, Digitalized? Nice to see you, man. Hope you're doing well. Are you still working through the XV6 2022, by the way? All right, let me just slowly get into this. Let me just build and see if this builds. So this does build. Let me just get my VS Code out here. Right, so I have my panic. I'm actually not seeing my panic. I should have oh, here it is. Okay, but the reason I disabled the panic is because I was following these instructions, which told me to run a particular test binary. Got sidetracked for 2 weeks, or STM32 word. Oh, nice. That sounds fun. I've heard of STM32, but I actually don't really know what it is. Is it like some kind of microcontroller? Or is it more capable? Like, can you run like Linux on it or something? I've heard it's pretty popular for like hobbyist embedded stuff. Yeah, so this is saying set up the receive queue, configure it, no long packets, no multicast, no interrupts, and strip the CRC. I'm pretty sure I did all that. By default, the card will filter out all packets. You need to configure the receive address registers with the card's own MAC address in order to accept packets. So that's what I did. Pretty sure that's what this part does too. But maybe there's a problem with how I did it. Yeah. You can hard code something. Be careful with the byte order. Yep. E1000 only supports a specific set of receive buffer sizes. If you make sure if you make your receive packet buffers large enough and disable long packets, you don't have to worry about packets spanning multiple receive buffers. Also remember that just like for transmit. Okay, yep. So pretty sure I took care of all of that. So now it says you can do a basic test, and it says you can run the test input thing. Test input will transmit an ARP announcement packet using your packet transmitting system call, which QEMU will automatically reply to. And that's because QEMU emulates this virtual network actually with some other stuff on it. And so QEMU will see an ARP packet going out, and apparently QEMU will be running some kind of other servers on this virtual network or devices on the network that will see this reply. So even though we can't really receive the reply yet, we should see some kind of message apparently saying a unicast thing matched our MAC address and match. If you see a mismatch, we got filtered out, which means you probably didn't configure RAL and RAH, which are, again, these are, let me get my manual out here. So many references to these things. I actually don't, they were kind of hard to find. Receive address low here. Yeah. So that's 5400. They were a little bit hard to find the constants for, but yeah, 5400 is this 1000 RA thing. Right. Make sure you got the byte ordering right and didn't forget to set the address valid bit and RAH. I'm pretty sure I did all of that. It's the top bit. We can see that. Did I take a screenshot of the? I guess I didn't. Let's just quickly. Yeah, it's documented here. So here's the RAH, RAL. What's up, Babu Deli? Hola, welcome. Yeah, so these are the docs for register, and we can see that the highest bits of the RAH register, which is supposed to contain the highest 2 bytes of the MAC address. Yeah, you just need to set this to 1. Determines whether this address is compared against the incoming packet. When set, the address is valid and compared. When cleared, the address is invalid and not compared. Okay. Hey Rico, did you just happen to stumble on this MIT CS or chose it for a reason? I sort of stumbled upon it. Originally I was using XV6, which is this really famous learning OS from MIT. And I was having a lot of difficulty with it because it was a bit too complete. But that's partially what's used by this course. But the main reason I chose this, so basically, yeah, if you start at XV6, you'll find that it's used by this course, specifically the 2018 one. But the course actually switches to this other OS called JOS a bit later, which is a lot better because it's not as complete. And so that's kind of how I went with it. Because I wanted to specifically learn x86 or do an x86 OS course. The newer version of this MIT course is RISC-V, and I didn't really want to do that. Here's the link to the course. Yeah. Okay, so basically that's all of that's to say, I believe I'm setting this correctly. All right, let's just do it. All right, how do I run this thing again? I need to do make this thing. Yeah, so what happened just now? So the OS booted and it that's interesting, that's new. Mac reg article. So the OS booted up. I still don't exactly understand why there seems to be 4 NICs on the system. But then we boot, and then we boot into user space, and we run this app, which sends apparently it sends an ARP packet. Yeah, and that looks legit. So what I'm doing right now is I'm looking at the PCAP that QEMU emits when you do network traffic. And so it's a the good sign is that it looks like some ARP data was sent, specifically from us. It's like an ARP request. 10.02.15, I believe, is our IP address. And we got a response from something on the virtual QEMU network responded to us. And this MAC address looks correct. 52.5.54.00 12.34.56. So that's at least a good sign. That means the transmission is still working, which it should, since we got that working in the last couple weeks. But the problem is that, well, I'm just going to take a screenshot just to document that this was working. Okay. And also, I'll take a moment to add some more room here. Today is 420. Happy 420. Episode 64. So we confirmed that ARP was sent out and a response was sent. We did not receive anything in the OS. That's what the situation is kind of looking like. So let's look into this. How? So I'm not seeing anything. Unicast, I'm not seeing unicast match. I'm not seeing unicast mismatch. Or am I? So it sends the ARP, and then we would see some kind of message here, and we don't. Maybe just to quickly confirm. So I was trying to build QEMU. I mean, I did build QEMU, but yeah. So it looks like QEMU is still building. I'm going to go and open my upstream QEMU just to make. Let me just confirm I really have enabled all of the debug logging. So for example, if I disable the TX logs, we should observe a difference. So I'm going to try to do that. I'm going to hopefully that worked. I comment out the TX. Pop over here. I rebuild. That should do something. I think that did it. I'm going to run this again. And we observe a change. It's no longer printing the TX disabled messages. So that just confirms that I am actually able to build my QEMU and have it be used and stuff like this. And so that gives us confidence that these RX filter, that might be the missing one. That sounds important, actually. That sounds important. Let's rebuild that. Okay, now let's try that again. Okay, okay. I'm not seeing anything. Okay, so it seems like that actually did not give us any more information, which is kind of unfortunate. I want to find match. Let's also just make sure that these log lines are even in the QEMU that we're looking at. I do not know what I'm looking at. This is some like strange syntax. Okay, but it would appear that these messages are in this version of QEMU. So what can we do about this? I mean, I'm just going to brainstorm a couple options, like how do I'm going to take a screenshot first off. So no unicast match nor mismatch error log. Wrong with the unicast etc. Maybe, so basically one idea, maybe there's something wrong with how we initialized. Wrong with how we init the NIC. So we could audit that. Something else we could do is just look at XV6 2022 and copy them. Because so basically we could look at another OS and see how it does this initialization. I want to avoid doing that if I can, because it would be very satisfying to be able to just initialize the NIC purely based off of the docs. But if it's too hard, I won't do it. Just look at it. But let's just take a moment to see. Also, for the record, I also previously already looked at the other OS and sort of copied a bunch of stuff. One easy thing I'm going to start with, I'm going to take away some of my other prints. I actually added a few other prints to QEMU that I don't need anymore. They're not really that useful. Or rather, maybe I'll comment them out. It's e1000.c. PMA read. We don't need this. Oops. I'm just looking at this line, RCTL 127 Mac Reg blah. Let's find where it prints that out. Maybe that would give us a hint at Mac Reg. So this this function runs also. What's this? Okay, this function runs when we set the control register, and that's what we're doing here. RCTL. Oh, yo, Lizard, what's up, man? Long time no see. Hope you're doing well. Yeah, I want an update. How's all the Verilog going? How's all the embedded stuff going? Right, so that QEMU log line comes from when we do this. RDT. And then our so I find this a little bit confusing. It seems like it's printing out RDT. RDT is like what, the tail register? RISC 5 core almost done, nice. And problems with USB on STM32. Dang, it sounds difficult. So it prints out seems like kernel hacking has come far. I'm trying my best, but slow and steady as always. Yeah, we're working on networking. We got transmission working, and now we're flipping it over, working on the receive side, trying to receive data on the network. And I'm kind of stuck as I usually am. So what are we seeing here? This, like, very unintuitively, it says RCTL, but then it prints RDT, which is the tail register. And for us, we're seeing that it prints 127. And that's correct, because our ring buffer is of length 128. And as I was kind of visualizing over here, we initialize it such that tail is all the way at the end. And we fill the buffer as completely as we can, which means tail is all the way at the end at index 127. So that looks right. And then it's printing out the RCTL. We can double check that. 4, a lot of zeros and a 2. It would be really cool if I could find where they document CTL. Receive control register. .4. I don't know why the search doesn't find it. 13.4. 22. All right. So this is worth highlighting. One thing I've learned is that you need to have an industrial strength PDF viewer if you're going to work with these kinds of manuals. Like, I was trying to do it with the preview app on Mac. It was not cutting it. I'm really benefiting from an industrial strength PDF viewer, like Skim is what this one is called. Okay. So it's a 32-bit register. We enable the second bit, hence the 2. And we pretty much, we didn't do anything else. Except for one other thing, which is this like strip CRC thing. And we enabled that, which is sec RC bit 26. And that's just a constant I made right here. And bit 26 is just because I'm lazy. But there's no way. Right, it's 4. 40, yeah, 4 all the way at the top. Actually, no, it's 400, then 4 zeros. That's what we see here, right? 400, then 4 zeros. Okay, so that's looking approximately right. Ocular is my best friend. Okay, thanks for putting me on. Ocular PDF. Let's check out. Let's just take a quick moment. Ocular PDF. Whoa. Nice, this looks good. All right. The card will filter out all packets. If you see a unicast mismatch, the E1000 filtered out the packet. I would even be overjoyed to see this, because that means the filter is like engaged, but it's just rejecting the MAC, which means we just set up the MAC address wrong. But like I don't see that. Okay. So maybe let's just quickly audit for, are there any other important bits here? I mean, there was also, let me see if I screenshotted it. There was some interesting stuff in the docs here. Packet address filtering. This was towards the beginning of the docs for the receive side. Hardware stores packets subject to the following filter modes. The following modes are supported. Exact, unicast, promiscuous, multicast, and I think that's what we're using. We're using exact unicast right now. I'm also still slightly suspicious that I just don't have the debug flag set up correctly somehow. Am I missing something really important? What's up, useless? Say yo, happy Easter. Yeah, happy Easter to you too. IO, TXON, like any. I'm enabling a lot of these. RX error, TX error, TX RX interrupt. Maybe I will actually just sort these by just to make it easier. RX filter is definitely engaged, so, and we are definitely using, right? Okay, I have an idea. I'm going to store bad packets. I'm going to enable unicast promiscuous mode. When set passes without filtering out all received unicast packets. Otherwise, the Ethernet controller accepts or rejects unicast packets based off of that. So I think if I enable this, we should maybe see something because it basically disables the filter. That it's still a problem that we don't see, like, we don't see the log message under normal circumstances, but at least maybe this can give us a bit more information about what's going on. So yes, the ever famous promiscuous mode. That's literally what they call it here. Okay. It's bit 3, right? Bit, and we have a bit. It's bit 3. Let's try it. Promiscuous mode. Okay, we can see that something happened because the RCTL register is different. It says A now instead of 2. But so there's still nothing. What does Wireshark say? Wireshark has not changed at all. Still just the ARP message and the ARP response that we are like not seeing. Okay, so I'm just going to document this. So didn't work. Still no log messages. Yep. That's unfortunate. Store bad packets. Multicast. What if we enable everything? What if we enable any kind of promiscuous mode? Still nothing. Okay. Long packet reception enable. Loop back mode. Okay, some interrupt. I don't know. Reserved multicast offset. Broadcast accept. Bam. Let's enable broadcast. I don't really know. Maybe it's a good time to just learn some basic, refresh on some basic networking concepts. Like what do unicast, multicast, and broadcast mean in networking? I'm gonna ask ChatGPT. Okay. Unicast, one-to-one communication, one sender, one receiver. Okay, pretty standard. Multicast, one-to-many, but only to interested or subscribed. You send data to a multicast group. Okay. One-to-all communication. Data is sent from one sender to all devices on the network. Example, ARP. So that would be kind of interesting, because if ARP is using broadcast and we didn't enable broadcast, maybe that could explain it. Let's give it a shot. Let's enable the broadcast accept mode. Wait, when set passes or does not filter out all received broadcast. Otherwise, it accepts or rejects a broadcast packet only if it matches through perfect or imperfect filters. Okay, so even if we didn't enable this, it would still be able to get through if it matches the filter. But since I have nothing working right now, I'm going to try this. So we got bit 15. All right, let's run it. Oh. Still nothing. So if you're wondering, this message comes from the transmit side, pretty sure. Man, okay, broadcast accept did not help at all. So clearly this is changing. Real quick, did I enable it even correctly? Is it possible I made such a ridiculous mistake? Enable is bit number 1. Right? Receiver is enabled when this bit is 1B. Okay. I'm pretty confident I did that correctly. RCTL, what? That's confirmed to be hex 100. All right, so nothing has worked, but I'll just keep enabled. Multicast promiscuous enable. Broadcast accept all enable. Yeah, nothing worked. Okay. We got a bit of a mystery on our hands here. What is going on? So I could always tap out and look at XV6, but I am going to try for 12 more minutes until the hour to see if I can get anything working here. What could I try? I could audit my code here. I mean, so in general, all this code is running in the E1000 init function. And so like it would be kind of like, for example, you could imagine that maybe I made a mistake where the receiving happens like way late or something. And so it sends out the ARP transmit, but it's not even ready to receive yet. But I'm pretty sure that's not the case because I just initialize the receive side immediately when I initialize the transmit side. And so the NIC should be like really fully just brought up. This is where I am setting MAC address, but we're not even seeing the mismatch message. And this is the buffer low high. That's super standard. That's just exactly like we did this above for the transmit buffer. Set the head and tail. We fill the buffer by just iterating over every entry, and we just set two things. We set the backing buffer pointer and we reset the status to 0. And then we enable the NIC. So that's what's happening. Maybe we can look at the status register. Is there maybe some interesting information in the status register? Link speed. This is like, okay. None of this really seems interesting. Device control register. What is this? This is CTRL0. As far as I know, I am not touching that at all. Control the major operational modes. Invert loss of signal. Yeah, there's so much stuff here. Force speed. Force duplex. Device reset. Flow control. I could not imagine writing a production driver for this thing. This is so complicated. Okay. any other ideas about how to proceed here? Actually, you know what? It's been over 20 minutes. Let's take a quick palm tree break. Be right back. Okay, what can we do? We could reread the documentation. Here. We could reread general configuration, receive initialization. We could reread this and see if there's anything that's not correct. So this thing I commented out because it seemed like QEMU did not implement it. That was this for loop. They're just writing a bunch of zeros into memory. It seemed like QEMU did not implement this because it just had MMIO unknown right. So yeah, gonna keep that commented out. I'm not doing any interrupt anything at all. I'm not using any thresholds. I am doing this. The size in bytes of the descriptor ring. I did do this size of, yeah. Yep. Program the RCTL with appropriate values. Not doing long packet enable. Loopback mode should be set to 0 for normal operation. Okay. Configure this. The broadcast accept mode, right? We already saw this. Configure the receive buffer size to reflect the size of the receive buffers. We're using 2K buffers and yeah. We're using 2K buffers, and I'm pretty sure that zero equals 2K. So we're just using the default. Strip this thing, blah, 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 blah. Okay, so nothing worked. Nothing worked. I think it's about time to look at XV6. I wish I had a better idea of what to do from here, but let's just take a look at XV6. So Okay, here's XV6. XV6 2022, which features like some very similar stuff here. Receive initialization. So RX ring, they do it very similar to me. Except they use 16, okay. They do it very similar to me where they have, yeah. Seems like just like the buffer of the ring buffer and then also some backing buffers, whatever this is. Memset everything, and then they, oh man, I missed a bunch of chat messages. Hell yeah. What's up, Afnan? Late for the test one. Good to see you, man. The Art of War, hello. I'm struggling, but otherwise good. Thank you. What's up, Ryan? Such a chill space. Thanks. Are you ARPing for IP that would actually respond? Yes. Yeah. So QEMU would respond. What's up, Zara? Happy Easter. Nice to see you. All right. Let's look at how XV6 does this. It's doing something very similar to us. It's looping through all of the received descriptors. It's actually allocating memory somehow for the backing buffer, and then it just sets the address pointer to some memory. And apparently, again, I think I was confused by this previously, but they seem to be using a virtual address for the buffer pointer, which I don't know if that's correct. But I mean, it's in this OS, so maybe it is, but everything I've seen says you need to use a physical address there. Then RDBAL points to the ring. That's exactly what I have here too. They don't even set RDBAH because we're not on 64-bit. Head and tail get initialized like this. I'm doing the exact same thing. And then the length is the size of this thing, so I'm doing the same thing. So that looks totally the same. And then I think I already kind of looked at how to do this last time, but yeah, setting, get this. So setting the first 4 bytes of the MAC address, 12, 00, 54, 52, followed by, at one location higher, at one word higher in memory, we set the remaining. I did it exactly the same way as them, 56, 34, and then shifted with the 31-bit all the way over. Multicast table, they did that. Okay, that's transmitter stuff. Then and then they're setting the control register, and they set the enable bit. Let's take a look at where these constants are defined. What's up, Chivo? Welcome. All right, let's take a look at where these constants are defined. So EN, this is 2. They're using BAM actually. So first off, theirs looks very similar to mine. It has enable, which is 2. And then they're actually using BAM, size 2048. I believe that's just zeros though, and then sec_rc. So let's find BAM. They just actually have these big numbers there. Yeah, and then size 2048 is just zeros. And then sec_rc is the 400 and then 4 zeros number. Yeah, so that's like, it's not very encouraging because I didn't find any difference between, I did not find any difference between how I'm initializing my receive side and how they're and how they are doing it. Maybe the error's on the transmit side. So Bakfer, that's a great idea. I kind of ruled that out because when I run the kernel, it produces it produces a network traffic dump of the network activity that happened. And we can actually see that some ARP requests were sent. And ARP request was sent from us, actually, from the transmit side. And then it does actually, it really seems like the reply was sent by someone on the virtual network. And then I think this third thing is like kind of like random. I think that actually corresponds to this log line with the 110 bytes. I think that there's some service on the virtual network that's like sending out ICMP messages at some interval. So we can ignore that. So I have some confidence that the transmission is working correctly, but good idea. So now things got really real. Now I'm not quite sure. My main idea, I guess, would be to add some more print statements to QEMU. Add prints to QEMU to try to debug why we're not seeing anything. So we already tried this. Didn't work. We seem to be doing the exact same things. So yeah, we could go into QEMU and add some prints. I kind of want to avoid that. Because I don't really want to get into all the internals of QEMU. But if there's no other options, we'll have to do that. Sub Art of War, I have a question. Currently, I'm a full stack dev. I want to learn C. Can you guide me from where I should start and climb the ladder? Yeah, I have a couple recommendations that I always give to people. I forgot the command, actually. I have like a chat command. I think it's the resources chat command. And then just personally, I've just been recommending that everyone checks out pwn.college. Which is a little bit security oriented, but that's the highest quality like learning materials for low level programming that I've seen. So yeah. Okay, so add prints to QEMU. Go back to Wireshark. what's the MAC of the responder? Does it match your filter? Okay, so the responder has some like random MAC with a bunch of 2s, and it is replying to our ARP message. So yeah, I think, and the way the filter works, as far as I understand it, we just put in a filter for our MAC address. And when stuff comes in on the network, the NIC checks if it's meant for us and might filter it out. But the interesting thing here is either way, if it matched or if it got filtered out, we should see a diagnostic message. It says, if you see this match thing, that's a good sign. If you see a unicast mismatch, the E1000 filtered out the packet, which means you screwed up. Let's just go back to QEMU and see one more time who is producing these messages. Unicast match. I actually want to find out, I simply just want to find out which log level is going to be printing this, just to make sure I have that really enabled. And apparently I need to learn how this syntax works. Oh man, tracing the RST syntax. Can I preview? Okay. Using trace events, declaring trace events. Here's what a trace event looks like. Maybe I actually don't need to care about this. Maybe I can just grep for this. Let's take a look at where this is triggered. Okay, so yeah, I know Pone College, so should I start with Security Systems course? I don't actually know the specific courses because I haven't actually done Pone College, like all the in any level of detail, but they have courses on C programming and kind of as a setup for reverse engineering, I think. But I would just say look through the courses they have available there and see if anything piques your interest. And just go with that, and just try to find some stuff that will get you introduced to C, basically. Okay, so the good news is that there's not that many places, and the great news is that it's pretty much specifically just like this place, basically. And we can start out by just adding a print message here. Let's call it RX group filter. So I don't know what I'm doing, but I'm just going to add this. Do we see anything? RX group filter. Yes. We see something. That's a win. That's a very, very small win. Okay. Okay, we got another palm tree break. Be right back. Feel free to stand up and get some water and do some stretching. All right, so this is actually kind of cool. This is a bit of a lead. So now we are looking at the place in QEMU. We're looking at the place in QEMU that decides if data is like valid. To be processed by our NIC based on our configurations. So you cast match. I'm just gonna add some of my own prints at each of these places just to see. I mean, and I'll add one right here. I have a sneaking suspicion that this might be being triggered. Bam, match. Let's check it out. Okay. Nothing. Arcs group filter gets printed and then nothing happens. So is it one of these? Because we technically did enable all this stuff. Still nothing, okay. I'm just gonna spam print statements everywhere. It would be cool if I could debug QEMU. I kind of don't want to try that test. So I'm just print debugging, but I feel like this is getting somewhere. Do you use XV6 as a reference? Sometimes, if I'm kind of stuck, yes. But that wasn't very helpful. Oh, I'm stupid. I'm not rebuilding QEMU each time. Okay. UPE match. That's why we're not seeing anything. Because it hits the UPE match. So let me disable that. Yeah, there's just simply, let me just disable all of this stuff. What happens now? Ucast match. Yeah. So our homegrown print actually worked, which is incredibly annoying because it means the problem is just in like I just didn't enable the logging correctly or something like that. Harp should be broadcast. No. I guess so. That is what ChatGPT said. It said ARP should be broadcast. So that means it should have hit here. So let's try it. But we did not see that hit actually. Let's just come back one more time. We enabled the BAM mode. And what do we see? It still says ucast match. Is bcast, right? That's interesting. I can't explain that, but Bakafer, I think, like, it seems like you're right. Like, I feel like we should be seeing. Oh wait, yeah, thanks. I am. Yeah. How do I remember to do that? Like, thanks. All right, that did not. Is broadcast Ethernet address the destination? It's checking this on the destination. The destination address. So I don't know enough about this. I also kind of don't care, but maybe that's not hitting because the destination is just our normal MAC address and it doesn't qualify as a broadcast address. Something like that. Just to be completely sure, let's run it one more time. It's still just saying ucast match. What's up, Kenan? I missed 60 weeks worth of videos. What did I miss? Honestly, not that much. Just like me learning about how an OS works. We got the boot process working. We got virtual memory going. What else did we do? We got the file system going. We got IPC going. And now we're getting networking going. So yeah, never too late to join. Welcome. But yeah, it's a lot of video content. And it's pretty much all just like this of me like figuring out stuff. Yeah, but anyway, okay, this is a good sign though. Ucast match. So that means it actually did match. It is just not triggering the actual print for some reason. So maybe I need to enable tracing. Let me just ask ChatGPT about this. I enable tracing in QEMU such that it okay, also maybe this is a crazy idea, but okay, I was just checking that the message hadn't come through like the VGA console for some strange reason, but no, it just comes through here. Okay. Prints log lines when certain trace points are hit. For example, the net trace points. Maybe I can even give it an example. Like the holy crap, do I need to? Did I not? Create a file. I just want the trace event to be printed out where QEMU's logging normally goes in the command line. You got to be kidding me. Did no one trace? Dude, no one told me about this. To lab. All right, let's look at the updated lab driver trace. I'm not seeing anything. Trace. Wait. Network stack. Maybe I missed something. So Baka, that particular instruction, actually, with the make with this debug and all that stuff, that only applies to this like special QEMU that they prepared for in 2018 or whatever. It's like a QEMU like fork that they made, and I've kind of recreated that locally in my QEMU, but in a very in like a way simpler way. So in theirs was a bit more sophisticated, and they allow you to enable and disable the debug flags at runtime, and I am doing it way simpler, and I just am like statically enabling the flags that I care about. So that should not matter for me. So just out of curiosity, if I grep in xv6 for trace, I don't see it still. But it's completely possible that I did not like, or you know what? Let's check out the, so this is a bit of a divergence, but just for general understanding of how like QEMU works, let's take a look at their fork. So let me, how can I do this? I will be right back. QEMU MIT. So here is the MIT version of, wait, no, trace. Actually, no, I have no idea what I'm doing. So I was thinking I could look through their version of QEMU to see if they like have pre-configured it in some way, but let's forget that. So I actually still am interested in learning how this QEMU tracing works though. So I'm going to follow these instructions and detrace. So branch they for, yeah, maybe. Well, I mean, their fork is super old. It's like 6 years old, and the QEMU that I'm using is like a more recent one. So the diff might be kind of large. But let's just out of curiosity, let's try following these. So is there any default setting for? Oh, I see. Yeah. Diff where they branch just to see the changes. Yeah. Sorry, I misunderstood. Yeah, totally. Maybe. Let's get K. I don't know. Oh, unfortunately, my clone only has. It's like a shallow clone. Also, this thing. Or is it? Yeah. But it's on GitHub. Wait a sec, it's on GitHub, I think. So we got to go to tools and the QEMU somewhere here. And then it's a patched QEMU, something, something, something. And there are changes. E5B, yeah. Actually, yeah, wait, can I do this all in GitHub? How do I diff stuff in GitHub? Can I like, diff? No. How do I compare? How to diff in GitHub? Comparing commits. You add compare, okay. I'm going to, thank you for the suggestion. I'm going to copy this EB5 thing. I'm going to compare master. Right, so this is actually a fairly short diff. And this, like, so this is the part that's kind of relevant. And that's where they convert these debug flags to be runtime toggleable. And that's like all this environment arg parsing stuff that happens. And I think the rest of this is completely unrelated. It's like completely unrelated. Yeah, so that was interesting just to check, but I did not see anything too interesting there. Okay. No trace data is produced. Okay. So just for fun, let's try this. So we need to configure. Enable trace backends log. Right, after building, you can confirm what trace backends are compiled in. Oh, that would be great. Let's even just do that right now. Trace help. Match. And actually, I don't know what happened, but it seems like a bunch of these things are available. Trace. Specify tracing options. Enable pattern. Events or enable equals pattern. What if I just tried enabling this? That means I need to go to my make file, find the QEMU part of this, and we're going to add another QEMU option. Trace. Trace. Enable. Wait, what? And then we go over here and copy this. Still didn't work. I don't want to spend too long on this, but trace enable. Enable tracing. If no backends are explicitly selected configured, we'll default to the log backend. Okay, I think ChatGPT hallucinated then. It was telling me the NOP one is the default. Trace, what about this? All right, palm tree break, 20 seconds, be right back. All right. Wouldn't hurt to set it explicitly. You know, let's just do it. Yeah, I got my configure command line all set up here. It's kind of slow, actually, pretty slow to configure. It is building something. So, but yeah, this output comes from the log backend that's enabled by default when this is not explicitly specified. So we should be using the log when patterns are used. Let's configure to sort in the file -- trace. Let's try that. I want to move this out of the way. So we just need trace, QEMU upstream. Still nothing. Set it to E1000 everything. Yeah. Just like literally anything, right? And we can see the command line is right here. Maybe my quotes are messing it up, but wait, no way. This thing allowed quotes. That is truly very annoying. Like, it's not really worth spending the time here, except it would be even more annoying for me to like manually put have to put my own print statements everywhere. Yeah. So that's why I'm sort of fighting to do this. Quote expansion, try without for giggles, maybe try something else besides E1000. Good idea. All right. Let's just try. Okay, I'm just going to try the actual text here, just in case that does something. No. Filter, ucast match. Anything else in the docs? Trace events, blah, blah, blah. This is the simplest backend. Turns trace events into debug printfs. Yeah, okay, what about I don't know, yeah. I mean, it gave us a couple example ones right here, right? What about memory region obsolete? I don't know what that does, but I wonder that that weirdly hung for a very long time when I wonder if make is doing something, is like interfering. It's hanging for a super long time. And if I delete this, what happens? Is it faster? It's way faster. Yeah, okay, wow. Nothing I'm doing is like working. Trace, right? What was that thing I could do? I could do trace help. What if I give it an invalid trace point? Did it react to this? Trace event does not exist. So that's at least kind of a good sign. Similarly, it also warned me this does not exist. So if I give it something that does exist, okay. Quote this. QEMU trace not working. QEMU simple tracing. How do you simple? So the interesting thing though is when I enable that extremely expensive trace, like memory region ops read, it takes a lot. So maybe, wait. Yo! Oh my god, there it is. QEMU.log. What the hell? I think the make file has a -d. I mean, it has a -d, which was diverting everything to that file. Holy shit. Okay, I mean, at least we kind of figured that out. What happens if we don't do a -d? Who was even defining the -d? .log. Oh my gosh. I'm just gonna, yeah. It was still there. Oh wait, because I copy and pasted it. Okay. Yo, there we go. Look at that massive, okay, but wait a sec. Okay, so now, all right, wait a sec. So now, yeah. So now when I run the program, we get a million of these, or we get actually a couple of these prints. But interestingly, we did not, and is there a -d here? Not that I can see. All the way back here. So time to delete the -d thing. There we go. There we go. Holy crap. I feel like I just wasted so much of my life. At this point, I've wasted so much of my life with stupid configurations. Wow, okay. So that is cool. I can't believe I used this entire week just to figure out that QEMU was redirecting the output to some log file. Okay, so this like worked. What's up, Krishna? Hi, bro. So this worked when I'm running it, like I'm running it just like on the command line right now. Let me get it working in my make file. So I feel like it should have worked here though, right? But for some reason it's not. It didn't appear there. And so, yeah, it might be the std error something. So we can see that there's no log file in sight, but our trace things are there. And also the memory ops one is working. If I remove QEMU.log. Thank you, Krishna. Appreciate it. Okay, now this is getting into really crazy levels of stupid territory. You aren't the only one that wasted his life. I wasted hours to figure out how hex can turn on LEDs. I'm like, change one of your test printf to print to standard error. See if it disappears. Yeah, good idea. But the interesting thing here does like make, do I need to like redirect standard error? At least so when I do that, it goes super slow again. Ah, interesting. Wow, this file is huge. This file is enormous. Yeah, change one of the prints to a print. Let's do that. QEMU upstream. Match. Was it bcast? How do I find? What did I say? Ucast match. Ucast match. How do you print to standard error again? It's like fprintf, right? And fprintf. Which lets you pass in error. Dude, I literally don't. How to It's been so long. How to print to std error with fprintf. Std error, okay, easy. It's like this global variable, right? Let's recompile QEMU and let's. So that's interesting. So sorry. So that's interesting because the std error thing even gets printed. So what is going on? So my manual command line works. I'm just gonna stash this away somewhere. You know what, maybe I can diff it, echo. Ugh. I kind of want to diff, like, is there any way no, it's like I was going to diff the command lines between what make does and what this does, but they should be super, super similar. Holy crap, my mouse doesn't work. What? Oops. My FFmpeg. Oh shit. Okay, wait. I just messed up with tmugs. Okay. Why does my mouse... For some reason my mouse is no longer allowing me to scroll up and down in tmugs. That's unfortunate. You cannot set forwarding rule. Wait, what? Sorry, okay, new terminal. All right, new terminal window. I don't know what happened there. Oh, come on, okay. Okay. Okay, there we go. We're obviously not seeing it here. But if I take this exact command line and paste, that did not work. Why? Wow. What the hell is going on? Oh, matches for wildcard. Okay. This is where I need to go in and add. Dude, I'm so confused. Hello. Okay, good. Wait. There's just like this one magical situation where it works. All right, let's. What about so let's remove this. Maybe it's the ops, maybe it's the ops read. Maybe that is messing everything up. It might be something as simple as that. That was it. Oh my gosh, I think it was something as simple as like that ops read generates an insane amount of output. And that is screwing up something with how make streams its output. Let me catch up on the chat. Ugh. All right. Replace the S with an N. One I learned from you is adding breaks at 20 minutes and everyone regular stretching. I installed a small application. Thanks. Yeah, it's a good idea. I like it. You might have resized and screwed up word wrap. Yep. I mean, a thing which is capable of passing calls from DLL to Windows, Gas, VM, Linux. Cool. You can't define trace multiple times, I bet. It seemed like you should be able to, based off of the website. So what I'm going to just do now is this thing, and let's run it. Yeah, we get, that just instantly works. Okay. That just instantly works. Check out this. Check out all that juicy log messaging that's happening right now. That's great. That was painful. That was very painful, but I'm going to call that a win. So now we get to go through QEMU upstream, and I'll just go through and like delete some of these lines. I don't need this anymore. I don't need this. Don't need this anymore. Don't need this anymore. I'll just leave these in just for fun. But wow, what a day. Anyway, what did I learn today? I learned that everything was working, basically. And it was just a logging problem. So let's take a quick look at what's next. I'm gonna sign off in a bit, but fixed while testing. Yeah. I'm gonna sign off in a little bit. Let's take a quick look at what's coming up for us next week. Okay. I basically did not make any progress except for making these log messages show up. We got that working. And now what's next? Now you're ready to implement receiving packets. To receive a packet, your driver will have to keep track of which descriptor it expects to hold the next received packet. Hint, depending on your design, there's probably already a register keeping track of this. Similar to transmit, the documentation states that the RDH register cannot be reliably read. So in order to determine if a packet has been delivered, you'll have to read the DD status bit in the descriptor. If the bit is set, you can copy the packet data out of the buffer and tell the card that the descriptor is free by updating the tail. If the DD bit isn't set, no packet has been received. This is the receive side equivalent of when the transmit queue is full. There are several things you can do. You can simply return a try again and require the caller to retry. While this approach works well for full transmit queues because that's a transient condition, it's less justifiable for empty receive queues because the queue may remain empty. So basically, it might not be a good idea to like spin on receiving. The second approach is to suspend the calling environment until there are packets to process, similar to IPC receive. Since we only have one kernel stack per CPU, as soon as we leave the kernel, the state will be lost. We need to set a flag indicating that an environment has been suspended by receive queue underflow and record the system call arguments. The drawback is complexity. The E1000 must be instructed to generate receive interrupts, and the driver must handle them. Okay, that's like kind of complicated. But basically, what's up next is actually receiving the data, like copying the data that we receive, and being able to do something with it. Your driver will have to keep track of which descriptor it expects to hold the next received packet. Let me just think about that quickly. Your driver will have to keep track of which descriptor it expects to hold the next received packet. So let's go back to our diagram. This is how it looks like right now. We initialize the queue to be completely full of these empty and available descriptors. And then let's say we receive some data. We receive 2 packets. Now things sort of look like this. These are not available and free anymore. So my idea was just to use the tail register. So when the function is going to be responsible for checking the state of the queue and seeing if there's any data available to harvest from the NIC. And so we enter the function, and it's just going to look something like, okay, starting from the tail, we like work our way until the head or something like that. And we see if any of these are processed. I guess the tricky part though is tail points is initialized to point at an invalid buffer. And so how do we know how to loop over these? Because when hardware, we should probably set the DD bit here. But we also Right. So basically, the way software is going to see what descriptors have data is it's going to start at the tail, and it's going to say, okay, is there a DD bit here? Then that means some data was, then it's processed by hardware, and control is back to software. And that works for example, for these two, but we reserve one descriptor of space, and we intentionally don't use it because otherwise the tail will just wrap around all the way to the head again, and I believe that makes the queue look empty. So that's why we were putting the tail all the way over here. But if we didn't set the DD bit, it would look like this. So what I think we need to do is initialize the DD bit on the tail, even though it doesn't have a descriptor, but then set its length to 0 or something like that, so that we don't actually do anything. Because the length is provided by hardware. It's written into the descriptor. So just as a little bit of a last thing we can do before we initialize all the descriptors, and then for the last descriptor, set DD bit and set length to 0. And I'm just gonna quickly sketch this out. Okay, RX descriptors -1. Yeah, so we actually don't need the backing buffer. And then what does one of these things look like? Buffer length. So length equals 0, and I guess the status. And what does the status look like? DD bit is the first bit, and so is 1. And so now from the perspective of this algorithm, it looks just like a descriptor that hardware has actually processed and put something in. And so the algorithm is going to be start from tail, and something like while the next one has a DD bit, process it, or something like this. We did a similar thing for the transmit. The transmit, it was just like a certain position. Or not. Yeah, for the transmit, we initialize the DD bit for every single descriptor to make it look as if it was available for transmission. But we actually just initialize the head and tail to 0. Right. All right. So anyway, next time we're going to get into all of this and actually processing data from the receive buffer. So I'm going to call it here. Thanks a lot for joining the stream. I'm just going to self-promote myself. Feel free to join the Discord if you like. Subscribe to my channel if you like what I'm up to, and I'll be back next week. So thanks a lot. See you later. Bye.